So far in Chapter 20, we have discussed the meaning of redox, reduction and oxidation, identified oxidizing and reducing agents in equations, and also discussed how to calculate the electromotive force, or E cell, for a voltaic cell or battery. In this section, we also want to establish a connection between Gibbs free energy, which we discussed in Chapter 19, and redox. The first main equation we want to take a look at is delta G standard equals negative N Faraday's E standard. And some of these letters we've seen before, some we have not. The G should look familiar to you. This is our Gibbs free energy. If you think back to our thermodynamics chapter, it indicates to us whether or not a reaction is spontaneous or not, based on the sign of delta G. N is the number of moles of electrons transferred in the redox reaction, so the number of electrons lost and then gained. F is a constant, which is called the Faraday. And 1 Faraday is equal to 96,485 coulombs per mole, and that coulombs per mole is really coulombs per mole of electrons. And sometimes when we use the Faraday, we need it to be to incorporate volts into the constant, and so it's also equivalent to 96,485 joules per volt mole of electrons. And a lot of times the chemists leave the electrons out, but that's what the moles represent. And as you are looking at this equation, we have talked about in Chapter 20 that this E cell is really the voltage, and we calculate that by taking the reduction potential of the cathode, where reduction occurs, minus the reduction potential of the anode. So cathode minus anode. The Gibbs free energy, we use Appendix D for, no, Appendix C. You guys have so many handouts now. Appendix E is the new one we received in this chapter. We would use that for voltage, and the old handout, Appendix C, which has delta H, delta G, and delta S, the thermodynamics quantities, that would be used to calculate delta G. One of the things to think about as you look at this equation is you might notice the appearance of this negative sign in the equation. And the reason that's there, if you think about what we've learned and discussed about free energy and redox, typically we would say a reaction is spontaneous if the sign for Gibbs free energy, or delta G, is negative. And if you look on the right side of the equation, if we look at the sign on E cell, or for the voltage, we know that that's a positive number if it's a spontaneous reaction. And we have to have these two situations on the same page, so to speak. We need them to be in agreement. And so if you have a spontaneous reaction, delta G is negative, E is positive, and so we need that negative sign in there to kind of clear all that up. Now, as you know, when I talk about scientists, I often like to include pictures of them. This is a picture of Michael Faraday, for which the Faraday's constant is named. And it's interesting if you Google him, because this is a very common picture that pops up a lot. And then there's also this one of him, and it appears that science has really taken its toll on this guy. He looks a little forlorn here in this image. Anyway, let's take a look at example number 1. On your handout of lecture examples for sections 20.5 to 20.6, example 1 says calculate E cell, or E standard, and delta G standard for the following reaction. And we're going to want to focus on that new equation, delta G standard equals negative N. And by the way, the Faraday's is sometimes written as a script capital F, so if you see that, that's what that's about. And then we have E standard. So we're going to start by focusing on what we've been working on in this chapter, chapter 20, and that is E cell. To figure out the E cell, we do cathode minus anode. And so you should start by finding your green Appendix E handout and determining the reduction potentials for the two half reactions given in this problem. And you can see that we are dealing with silver, and we are also dealing with oxygen. And so on your green handout, go ahead and locate those. We'll pause the video here for a second so that you can take a moment to find those. And hopefully you came up with the following. If we start with the silver, silver is going from 0 oxidation state to +1. And in order to do that, it would have to lose electrons, which is oxidation, and oxidation occurs at the anode. So the anode half reaction would be 4 silver solid yields 4 Ag plus and 4 electrons. Now that half reaction looks a little bit different than the way it is written on the green sheet because it's actually an oxidation reaction, so it's probably flipped. But when we do E-cell, we always want to stick with using those same reduction potentials. So that half reaction has a reduction potential of positive 0.799 volts. If we take a look at the cathode, remember the saying red cat, reduction occurs at the cathode. We have oxygen, O2 gas, plus 4H plus aqueous yields 2H2O liquid. And the reduction potential for that half reaction is positive 1.23 volts. As we've discussed previously, to determine the electromotive force, or E-cell, or potential difference, any of those terms that are used for the same thing, we take the reduction potential of the cathode and subtract the reduction potential of the anode. So using the two values that we've identified, that would be 1.23 volts minus 0.799 volts, giving us an E-cell of positive 0.431 volts. So we've answered one of the questions. And the sign for E-cell is positive, which indicates to us that this reaction is spontaneous, that it does happen on its own. If we continue with the second part of the problem, Gibbs free energy equals negative N Faraday's E standard. And so we substitute in our values. One of the biggest mistakes students make is the moles of electrons transferred. If you look at each of these half reactions, the anode has 4 electrons being lost, and the cathode has, oh, I guess I forgot the electrons in there. Oops. Sorry about that. Has 4 electrons being gained. Now some kids will add those together to get 8 electrons transferred, but that's not the case. Remember, one reaction is losing and one reaction is gaining, and either way you look at it, it's 4. Now, the thing to be careful of, if you look at the silver half reaction on your Appendix E, your green handout, it just simply says silver plus 1 electron to silver solid. But in order to get the electrons to cancel out when we add these reactions together, you do multiply that by 4. So the silver is losing 4, and then the other half reaction is gaining 4. So we would put negative sign here, 4 moles of electrons, and then the Faraday's constant, 96,485. And since we're going to be working with E-cell, which is measured in volts, we would use the label that is joules over moles of electrons times volts. and then put in our standard voltage, positive 0.431 volts. And if you crunch that out on your calculator, should get something like negative 166,340 joules. And the reason the label is joules is because the moles of electrons will cancel and the volts will cancel, and that will leave joules. Now that's an awfully large number to report as your answer, so more than likely delta G standard would probably be reported as negative 166 kilojoules. And once you finish a problem like this, we want to make sure that our signs make sense. When we calculated the E cell for the reaction, we came up with a positive number, which means that the process is spontaneous. When you calculate Gibbs free energy change, we get negative 166 kilojoules, and that has a negative sign, which also tells you it's a spontaneous process. So it's good that they are in agreement. The next section, 20.6, is titled the Nernst equation. And what we want to focus on here, so far we've been looking at a lot of standard conditions. In the previous section we had delta G standard and E cell standard, and we designate that with the little circle that looks like a degree symbol after E and after delta G. But we have to realize that there are plenty of lab situations that we are not at standard conditions, and the Nernst equation will allow us to calculate the E cell or the voltage when our solution concentrations are not standard conditions or not 1 molar. And to kind of set the stage for the development of the Nernst equation, we start with an equation from chapter 19. And in chapter 19 we had this equation, the delta G equals delta G standard plus RT natural log of Q. And this delta G on the left-hand side, this is non-standard conditions. So if we have gases and they're not at 1 atmosphere, if the molarities are not 1 molar, those would be non-standard conditions. As we worked through this equation back in chapter 19, we know that anytime we see this little degree marker, looks like a degree marker anyway, that this is your standard delta G. And that means we would get this value by taking products minus reactants from Appendix C. And I can't remember if it's yellow or blue, whatever handout we have that has the G's, H's, and S's on them. And then R is our gas law constant, T is our Kelvin or absolute temperature, and then we have natural log of Q. And Q, like any equilibrium constant, is always set up as products over reactants. And if we're working with concentration or with solutions, then that means that we have to use the square brackets that indicate concentrations. If we're working with gases, then sometimes they may use pressures instead. And if you compare these two equations, the one on the top and the bottom, we have simply substituted the equation from section 20.5, where Gibbs free energy is negative N Faraday's E. And in the first one on the left, it's non-standard, G, which means E is non-standard. And then after the equal sign, we see the two that have the standard markers. This is kind of a cumbersome equation, so we can simplify it a little bit. Here is a picture, by the way, of Mr. Nernst. Gotta love the glasses and mustache. But if we simplify, divide both sides by negative N and Faraday, since that's in all those terms, and simplify it, we get the Nernst equation. And this is the one I would definitely star in your notes. This is a widely used equation when you're talking about electrochemistry. And just to make sure you understand all the components. This E on the left-hand side of the equation, that would stand for voltage at non-standard conditions. And E with the little circle, E standard, that of course is standard conditions, which means we obtain that value by using Appendix E, the green handout, and we would simply take the reduction potential for the cathode minus the anode, like we reviewed previously. Keep in mind, if we imply standard conditions, your solution concentrations have to be at 1 molar. The N, as it has been previously, is moles of electrons transferred. And just be careful with this reworking of this equation. This is log of Q. It was previously ln, natural log, on the previous slide, so be careful, this is log. And Q is our reaction quotient. Keep in mind it's the same setup as K. Which means products over reactants. And while we don't have to use any ICE tables for these, we do need to understand how to at least set up our products over reactants in a basic equilibrium system. Speaking of equilibrium, one other way to manipulate this equation, if you happen to be at equilibrium, rather than lying to the left or the right side of the equation, if you're at equilibrium, then we don't use Q, we use K instead. So sometimes we can establish a nice connection here between electrochemistry and equilibrium. If you can figure out your E standard and use it at equilibrium, then we can write another form of the Nernst equation. And so for a system at equilibrium, we have log of K equals N E standard over 0.0592. So sometimes you may be asked to determine the cell voltage, the EMF or cell potential, and again, cathode minus anode is the way that is determined, and that comes from Appendix E. Anytime we are working with standard conditions, then you're going to use an appendix or a reference table to determine that. N is still your moles of electrons transferred, and K is the equilibrium constant. So if you are doing a problem and they ask you to determine the equilibrium constant for a reaction, and you're dealing with electrochemistry, then I would start by finding the E standard and working through this equation to find your equilibrium constant. Keep in mind, once you have the right-hand side of the equation determined, if you want to get just the equilibrium constant by itself, to eliminate that log, you'll have to use 10 to the x to determine that value. We're going to finish up with one last example on your reference handout. It says, determine the E cell for the following reaction when Fe plus 2 concentration of iron plus 2 is 1.25 molar and zinc plus 2 is 0.75 molar, and they give us a balanced equation. I want you to notice when you look at this problem the lack of a degree marker or standard indication on E cell. So whenever you see that in a problem and there's not a standard, we know that the concentrations are not 1 molar and we do need to use the Nernst equation. And so if we take a look at the Nernst equation, which is E equals E standard minus 0.0592 over N log of Q, we had that a couple slides ago, we do have to start by using Appendix E. So if we first determine our standard E cell for this reaction, we'd have to find the reduction potential for the cathode. We've heard this a lot today, shows up in a lot of places, minus the reduction potential for the anode. And looking at this reaction, I can see that iron is going from a +2 charge down to a 0, and so it is being reduced. It's the half reaction for the cathode, and if you consult your reference Appendix E, the value for that should be negative 0.440 volts minus the reduction potential for, in this case, the zinc. The zinc is being oxidized from zinc with 0 oxidation state to zinc with a +2 oxidation state. So the half reaction, or half the reduction potential for that half cell is a negative 0.763 volts. So if you figure that out on your calculator, it ends up, being a positive 0.323 volts. And now that we have that standard E cell, we can use the Nernst equation. And our Nernst equation, E non-standard equals E standard minus 0.0592 over N log log Q. And if we substitute, we'd have 0.323 volts minus 0.0592. Now N is moles of electrons transferred. And again, the common mistake, I mentioned it earlier, that students make is they will add together the moles of electrons transferred in each half reaction. And what we want to focus on is just pick one. In this case, the zinc is losing 2 electrons, which then are then transferred to the iron, so it gains 2 electrons. So either way you look at it, it's 2 electrons. And then log of Q, Q is going to be products over reactants. And when we set up our Q, remember, anytime you're working with equilibrium, we exclude solids and liquids. We can only work with gases and aqueous. So in this case, if we do products over reactants, it would be the concentration of zinc ions, zinc +2, over the concentration of iron 2 ions. So Q would end up being 0.75, that's zinc, over 1.25. So if you plug that in for Q and go ahead and solve this equation, we should get a non-standard cell voltage of positive 0.330 volts. And so the Nernst equation, you can see it's not a lot different from the standard voltage right here, 0.323 volts. But by changing the concentrations, we do get a shift in that equilibrium system, and as a result, our voltage does change a little bit, and in this case, it increased to 0.330 volts. So that brings us to an end of section 20.6. Oops. Have a great day.